right now, the chair you are sitting on is, well, it's essentially 99.99% completely empty space.
Yeah, it is a profoundly unsettling reality to confront when you really think about it.
I mean, the device you're using to listen to this, the floor beneath your feet, even your own body, it is almost entirely nothingness.
Right. We navigate a world that feels so incredibly solid and dependable, but
But it's a lie. Or, well, an illusion. The only reason you aren't falling straight through that chair right now is because of this highly aggressive, invisible quantum housing market happening at the subatomic level.
exactly. That solidity is just a macroscopic illusion generated by microscopic forces we can't even see.
So welcome to today's custom-tailored deep dive. Today we are taking that comforting, orderly image we all learned in middle school, the classic solar system model of the atom, and we're just tearing it apart.
It's time to move past the idea of electrons orbiting a central sun like neat little planets.
Yeah, absolutely. We are using Eric Kua's really detailed lecture notes on atomic structure as our guide today. Our mission is to decode the quirky, unpredictable, but highly structured quantum architecture that actually builds your reality.
Because understanding atomic structure isn't just about memorizing a list of subatomic parts, right? It's about understanding why elements behave the way they do.
We're looking at protons, neutrons, and electrons, and how their interplay is literally what makes the universe tick.
And what's fascinating here is that by the end of this deep dive, you'll see how tiny, seemingly insignificant differences in microscopic energy levels basically write the rules of chemistry.
Oh, and we'll also see how nature sometimes prefers to just completely break its own rules for the sake of stability, which is wild.
Oh, for sure. The exceptions to the rules are the best part.
Right. So before we can understand how atoms interact to build, like the chair you're sitting in, we first need to know what's inside them.
The foundational building blocks.
Exactly. We have protons, which have a positive charge of +1, and neutrons, which have 0 charge.
They're neutral, yeah.
Right. And they both live in the dense center, the nucleus, and they both have a relative mass of 1. But then you have the electrons.
And they are a completely different story.
They carry a -1 charge, but their relative mass is, well, it's tiny. It's 1 over 1840.
Yeah, that mass disparity is the entire reason chemistry even exists.
Wait, really? The entire reason?
I mean, essentially, yes. Think about the nucleus as a heavy marble sitting right on the 50-yard line of a massive football stadium.
Okay, got the visual.
The electrons are essentially weightless gnats just buzzing around the highest bleachers. Because the nucleus is so incredibly heavy and immovable, the identity of the element is completely locked in there.
But those dynamic, lightweight electrons, they're the ones doing all the interacting.
Exactly. They're the ones moving around, bonding, reacting. They totally dictate the personality of the atom.
But since these particles are so incredibly small, how do scientists actually measure them? Because you can't just, put an electron on a bathroom scale.
Right. You have to use indirect observation. Chemists shoot these subatomic particles through an electric or magnetic field to see how they behave.
Okay, let's unpack this with an analogy from the notes. I love this one. Let's say you're rolling different sports balls across a room, and you have a massive industrial fan blowing a crosswind.
That's your electric field.
Right. So if you roll heavy bowling balls, which are protons and neutrons, they might veer just a tiny bit or not at all.
Because they're heavy.
Exactly. But if you roll tiny ping pong balls, or electrons, that crosswind is going to blow them wildly off course.
It's a great visual. Though the physics at play are an electromagnetic pull rather than just wind.
Right, sure.
The specific angle at which these particles deflect is directly proportional to a very precise metric, their charge-to-mass ratio.
Charge to mass ratio. Okay, break that down for me.
Think of the particle's electrical charge as the size of a sail on a boat. The electric field is the wind. The larger the charge, the bigger the sail, and the harder the field pulls on it.
Makes sense. And the mass?
The mass is the physical weight of the boat itself. The heavier the boat, the more sluggish it is to turn, regardless of how big the sail is.
Okay, so the notes have this specific math example that I want to go through because it makes this so much easier to visualize.
Let's do it.
So we take a standard hydrogen ion, H+. It's basically just a single floating proton.
Right, so it has a relative mass of 1 and a charge of +1.
Exactly. Its sail and its boat are equally matched. And in this standard electric field, let's say that specific ratio causes it to deflect exactly 6 degrees.
Okay, a 6-degree baseline.
Now, how do we mathematically calculate what a helium ion, specifically He2+, will do in that same field?
Well, you weigh the sail against the boat. A standard helium nucleus has a mass of 4 because it has 2 protons and 2 neutrons.
So the boat is 4 times heavier.
Exactly, making it incredibly sluggish compared to that single hydrogen proton. However, this specific ion has a charge of +2.
Meaning the sail is twice as big.
Right, so you have a sail catching twice the wind, pulling twice as hard.
But a boat that is 4 times heavier. So the sluggishness wins out.
Precisely. The mass dominates the equation here. Because the boat is 4 times heavier, but the pull is only twice as strong, the overall ability of that electric field to alter its course is cut entirely in half.
So instead of deflecting 6 degrees like the hydrogen ion,
The helium ion will only deflect 3 degrees. And this isn't just an abstract math problem. This is the fundamental tool chemists use to identify what they're looking at.
because by measuring the angle of deflection, they can literally reverse engineer the invisible physics of the particle.
Exactly. And this naturally brings up the concept of isotopes, too.
Oh, right, isotopes. So those are atoms of the exact same element, meaning they have the exact same number of protons.
Same exact massive sail.
Right, but they have a different number of neutrons, so their physical weight changes, but their chemical personality stays the exact same.
Which perfectly underscores the rule we just talked about. The chemical behavior of an element is entirely dictated by the electrons and protons, the charges.
So adding a neutron is like, what, throwing an extra sack of flour into the hull of our racing boat?
That is a perfect way to put it. It makes the boat slightly heavier, slightly slower. It changes the physical properties like boiling point or density.
But it doesn't change the size of the sail. The boat still catches the wind the exact same way.
Exactly.
Okay, so if these electrons are acting like chaotic ping pong balls, and they are so incredibly lightweight and easily influenced, where do they actually live around the nucleus?
Well,
Like, why don't they just crash straight into the positive nucleus or smash into each other and tear the whole atom apart?
and that is where we have to completely abandon that simple solar system model. Electrons absolutely do not orbit on fixed flat tracks.
So what do?
The space around the nucleus is divided into principal quantum shells. Think of them as different energy levels radiating outward. But within those shells, the electrons live in subshells, S, P, D, and F.
Right, the subshells.
And those subshells are made up of atomic orbitals. But we have to redefine what an orbital is. It is not a path. It is a three-dimensional region of empty space where there is a 95% probability of locating an electron.
A probability cloud.
Exactly. It's a game of quantum statistics.
And these probability clouds have incredibly bizarre geometric shapes.
They really do.
Like, the foundational orbital is just a sphere. That makes sense to me. Just a ball around the center.
Right. Very straightforward.
But then you get to the p orbitals, and they look like giant dumbbells. And they are highly directional, lining strictly along the x, y, and z axes.
And it gets weirder when you hit the d orbitals.
Oh, totally. You have lobes pointing diagonally between the axes, and then there's that notoriously strange dz squared orbital.
Along with a ring.
Yeah.
Yeah.
To me, it looks exactly like a dumbbell wearing a little donut around its waist.
It is a wild shape. But this geometric complexity exists for a very practical reason. These shapes are the mathematical solution to keeping negatively charged electrons as far away from each other as physically possible.
While still keeping them bound to that same central nucleus.
Exactly. And filling this strange microscopic real estate requires strict adherence to quantum rules.
Let's go through those rules because the notes lay them out so clearly. The most basic one is the off-bow principle.
Right. It simply dictates that an electron will always occupy the lowest available energy orbital first.
Like water flowing downhill, it's just the path of least resistance.
Yes, but once they reach that lower energy level, they run into Hund's rule.
Oh, I love the analogy for this one in the notes. The public transit analogy.
It's the best way to visualize it.
It's basically like getting onto a city bus. If there are multiple empty rows available, you are going to sit in a row by yourself.
Naturally.
You will always choose an empty seat before you awkwardly sit down right next to a stranger.
And electrons do the exact same thing within a subshell. If there are 3 empty p orbitals available, the first 3 electrons will each take their own separate orbital.
They fill singly with parallel spins before they pair up. They maximize their distance to minimize that electrical repulsion. But, eventually the bus gets full, the electrons are forced to pair up and sit next to a stranger.
And that brings us to the Pauli exclusion principle. Each tiny orbital can hold a maximum of exactly 2 electrons.
But wait, since they are both negatively charged, shoving them into the same microscopic region of space should cause them to violently repel each other.
Right, absolutely. The repulsive force is no joke. This microscopic repulsion is literally the reason you can physically clap your hands together and they bounce off each other.
Instead of your skin molecules just merging into one solid block.
Exactly. The electrical forces are incredibly violent.
So, how do two electrons survive in the same orbital without tearing each other apart?
The Pauli exclusion principle states they must have opposite spins.
But they aren't physically spinning like toy tops, right?
No. Spin is a fundamental quantum property. It generates a tiny magnetic field. One electron spins up, generating a positive magnetic pole. The other spins down, generating a negative magnetic pole.
Ah, so that opposite magnetic attraction is the only thing strong enough to counterbalance their extreme electrical repulsion?
You got it. It holds that tiny piece of the atom together.
Yeah, well, I have to push back on one of these rules here. Because in Eric Kua's notes, there is this apparent contradiction in how these energy levels fill up.
You're talking about the fours and third subshells.
Yes. So the off-bow principle says we fill the lowest energy first. As we build bigger atoms, we eventually fill the 4's subshell before the third subshell because 4 is supposedly lower energy.
Right.
But then the notes say the moment the 4's subshell is occupied, it is suddenly considered to be at a higher energy level than third.
Yes.
So if an atom needs to lose an electron, it loses the 4's one first. How does that make sense? How can it be lower energy going in but higher energy coming out?
It definitely feels like a paradox, but it perfectly highlights how incredibly reactive the quantum environment is. Let's use a real estate analogy here.
Okay, I'm tracking.
Imagine an up-and-coming neighborhood. That's our empty forest subshell. Because it's empty and slightly closer to the nucleus, the property value, or energy level, is very attractive.
It's genuinely a slightly lower energy state than the neighboring third subshell.
Exactly. So following the rules, the first electrons move in there.
They buy up the cheap real estate.
Right. But the energy gap between fours and third is razor thin. So the moment those negatively charged electrons physically move into the fours space, their presence completely changes the neighborhood.
Oh, because of the electrical repulsion they bring with them.
Yes. That repulsion alters the entire energy landscape. The property value spikes. That 4's subshell gets pushed to a slightly higher energy level than the third subshell simply because it is now occupied.
Wow. So when an outside force comes along to evict an electron, the highest energy, most unstable electron is the first one kicked out.
Which is now the 4's electron.
That is fascinating. The atom isn't just this static parking garage. It's a living, breathing energy grid.
It's constantly shifting.
And speaking of shifting and changing the rules, we have to talk about the rule breakers, chromium and copper.
Ah, yes, the exceptions.
Because with all these incredibly strict quantum rules, Aufbau, Pauli, Hund, you would assume every element follows them to the letter. But we have elements essentially cheating on the test to get a better grade and stability.
Because nature is intensely pragmatic, ultimate stability always wins out over the default rulebook.
So let's look at chromium, atomic number 24.
Right. If you mathematically plot its electrons using the strict Aufbau rules, its outermost shell should end perfectly with third 4 and 4's 2.
It should completely fill the 4's orbital, leaving 4 electrons sitting in the 5 available third orbitals.
But that's not what physically happens in reality.
No. Chromium actively unpairs its stable 4's orbital. It moves one of those electrons over to the third subshell.
It intentionally leaves a gap in the lower level to become 35 and 4's 1.
And copper does the exact same thing later down the periodic table. It shifts an electron to become 30, 10, and 4's 1 instead of leaving one empty slot in the d subshell.
Yep.
Why exactly does moving just one little electron from the 4's orbital to the third orbital suddenly make chromium and copper that much more stable? Why break a fundamental law of quantum mechanics for one electron?
It all comes down to symmetry. If we connect this to the bigger picture, think of a car tire that is slightly unbalanced.
Okay.
When you drive, that lopsided weight causes the entire car to vibrate and lose energy. It's chaotic.
Right.
But if you put a tiny lead weight on the rim to perfectly balance it, the tire spins flawlessly, minimizing friction and internal chaos.
Ah, and the third subshell has exactly 5 orbitals.
Yes. So by shifting that single electron, chromium places exactly one electron into every single one of those 5 orbitals.
It creates a perfectly half-filled, symmetrically distributed subshell.
And copper creates a perfectly fully filled subshell.
Wow. So attaining a symmetrical distribution of negative charge around the nucleus minimizes internal electrical chaos.
And minimizing that chaos always trumps following the sequential filling order. Symmetry is stability.
So if symmetry is stability and the atom is desperate to remain stable, what happens when we intentionally mess with that balance?
You're talking about first ionization energy.
Exactly. This is the measurement of what happens when an outside force tries to rip an outermost valence electron completely away from the atom.
It is essentially a microscopic game of tug-of-war. The positive nucleus is pulling inward, trying to hold onto its electrons, and the outside universe is pulling outward.
So what does this all mean? How do we predict who wins that tug-of-war?
It comes down to two major concepts: distance and effective nuclear charge.
Okay, let's start with distance. Like looking down a vertical group on the periodic table, say moving from lithium down to potassium.
Right. As you move down a group, the ionization energy drops. It gets significantly easier to steal an electron, because every step down adds an entirely new principal quantum shell. The outermost electron is physically further away from the nucleus.
The longer the rope in the tug-of-war, the weaker the atom's grip.
Perfect analogy.
Hmm.
But as you go horizontally across a period, left to right, the ionization energy generally increases.
The atom's grip gets tighter.
Because you are adding more positive protons to the nucleus, increasing the inward pull, but you are not adding new outer shells.
The inner electrons stay the same.
Right, meaning their ability to shield the outer electrons from that positive pull stays constant, so the effective nuclear charge skyrockets.
Generally, yes. But the truly interesting physics hide in the anomalies.
Always.
Because there are specific spots where even though you are moving right across the period and adding more protons, the ionization energy unexpectedly drops. It suddenly becomes easier to steal an electron.
The first major anomaly happens between group 2 and group 13.
For instance, moving from beryllium to boron. Boron has a heavier, more powerful nucleus, but it actually surrenders an electron much easier.
And that anomaly is the physical, observable proof that subshells actually exist.
Really? How so?
Well, in beryllium, the electron you were trying to steal is sitting in the spherical L subshell. But in boron, the outermost electron has just crossed over into the dumbbell-shaped P subshell.
Ah, so even though they're in the same primary shell, the P subshell sits at a slightly higher, more chaotic energy level.
Exactly. It is fractionally further out, making it easier to pluck away.
And then there's the second anomaly between group 15 and 16, like moving from nitrogen to oxygen. Oxygen has more protons pulling inward, but it is easier to ionize than nitrogen.
And this brings us right back to our bus seats analogy.
Oh, of course. Because in nitrogen, the three outer p electrons are happily sitting in their own separate orbitals. They have their own seats.
But oxygen adds a fourth electron,
And that fourth electron is forced to pair up and sit next to a stranger.
which creates massive interelectronic repulsion. Those two negative charges are trapped in the same tiny region of space, fiercely repelling each other.
So, because they are already pushing each other apart, one of them is practically eager to be kicked out.
Yes. The outside universe doesn't have to pull as hard to steal it, so the ionization energy temporarily drops.
The underlying logic is so elegant, but we need to look at what happens when you don't just stop at one electron. The notes have this data on the sixth ionization energy for these elements, and it is mind-blowing.
It really paints a clear picture.
So, to clarify for you listening, this means you've already ripped away 5 electrons, and now you are trying to pull away a sixth.
Right.
For oxygen, taking the sixth electron requires about 13,300 kilojoules per mole, which is just a massive scaling factor for energy.
Very high energy.
Fluorine requires a bit more, around 15,200. But look at this data point for nitrogen. To remove nitrogen's sixth electron, it requires an astronomical 53,300 kilojoules.
It's a huge spike.
It's nearly 4 times higher. Why is nitrogen holding on so desperately? What on earth makes it resist with such apocalyptic force?
To understand that massive spike, you have to look at exactly where that sixth electron is living.
Yeah, okay.
Nitrogen only has 5 valence electrons in its outer quantum shell. Once you violently strip those 5 away, the atom's a highly reactive ion.
So to get the sixth electron,
You have to breach the inner sanctum. You are pulling from the innermost first quantum shell, the 1s orbital.
the shell right up against the nucleus.
Exactly, and there are 0 inner electrons left to shield it. The shielding effect is completely gone. That electron is experiencing the absolute, raw, positive pole of the nucleus.
While oxygen and fluorine have 6 and 7 valence electrons, respectively, so when you take their sixth electron, you're still just pulling from the outer shell.
Right. Understanding where these boundaries lie, the effective nuclear charge and the shielding effect, are the master keys to predicting how violently or passively an element will react.
Which sets up our final incredible tool, successive ionization energies. We've been talking about pulling away a single valence electron or maybe a stubborn sixth one.
But what if you keep ripping them off, one by one?
Yes. Measuring the exact energy required every single time until the atom is completely stripped bare.
You end up with a line graph that acts as an element's ultimate undeniable fingerprint. It really is a map of the invisible.
Because naturally, every successive electron you remove requires more energy. You are trying to pull a negative charge away from an increasingly positive, desperate ion.
But the line on the graph isn't a smooth, steady climb. It features sudden, massive vertical cliffs.
And those cliffs occur the exact moment you break into a deeper quantum shell. It is exactly like peeling a quantum onion.
That's a great way to put it.
Every time you hit a new layer, it takes an exponentially massive amount of energy to peel it back. And this lets chemists play detective.
It's a masterclass in deductive reasoning.
Let's walk through the example from the text. We have an unknown element X plotted on a simple graph. It's just a line with 12 dots showing energy levels. How does just looking at a simple line graph of energy spikes let a chemist play detective and completely identify an element out of nowhere?
Well, you look at the graph for this mystery element. The first two electrons come off with a relatively mild increase in energy. But the jump from the second electron to the third electron is an absolute vertical climb.
Okay.
What does that physical data tell you about the theoretical structure? It tells you that the first two electrons were in the outer valence shell, and the third electron was locked in a deeper inner shell.
Therefore, element X has exactly 2 valence electrons.
Which means it must belong to group 2 on the periodic table. By simply counting the number of relatively low energy removals before hitting a massive spike, you are literally counting the valence electrons.
Okay, so we've narrowed down the column to group 2.
Then, you keep counting the dots. Electrons 3 through 10 come off with a steady, predictable climb in energy. But the jump to the 11th electron is another massive vertical cliff.
So you've just breached yet another, even deeper inner shell.
Exactly. So, mapping it out, you have an outer shell of 2 electrons, a middle shell of 8 electrons, and an innermost shell. That is 3 distinct quantum layers.
3 shells means the element lives in period 3.
So you look at group 2, you look at period 3, you cross-reference the table, and
Boom. It is definitively magnesium. You deduce the entire invisible complex architecture of a microscopic entity just by analyzing the resistance it puts up when you try to pull it apart.
And that is the true beauty of this framework. This raises an important question, actually. We so often talk about quantum mechanics, probability clouds, spin rules, subshells, as if it's all just invisible, theoretical math that only exists on chalkboards.
But it isn't.
No, it has tangible, observable proof in the real world. Those massive energy cliffs on the graph are the physical manifestation of the principal quantum shells.
And the tiny dips in ionization energy are the physical proof of interelectronic repulsion and subshells.
The mathematical theory perfectly matches the measurable physical reality.
It really makes you completely reevaluate the world around you. We started today by throwing out that comforting, flat solar system model.
Good riddance.
Right. We looked at the heavy, unmoving nucleus that anchors an element's identity, and the lightweight, wildly chaotic electrons that actually dictate its behavior.
We visualized bizarre, donut-shaped orbitals.
And we saw how pragmatic elements like chromium and copper will blatantly cheat the fundamental rules of the universe just to achieve the perfect symmetry of an even charge distribution.
Because symmetry is stability.
And finally, we learned how measuring the microscopic tug-of-war gives us a literal map to read the quantum onion of any atom. Thank you so much for joining us on this custom exploration of Eric Hua's notes.
It provides an incredibly different lens through which to view reality. And as we wrap up, I think there is one final implication worth considering for everyone listening.
Oh, I love a good final thought.
We've spent this time analyzing how the microscopic arrangement of electrons, their energy levels, their opposite spins, their desperate desire for symmetrical stability dictates every single chemical property of an element. But remember, everything we know and experience is built from these exact elements. Our biology, the DNA twisting in our cells, the physical chair you were sitting on.
Even the neurotransmitters currently firing in your brain as you process this information.
Exactly. So we've seen that the arrangement of electrons dictates every single chemical property. Since everything we know is built from these elements, to what extent are the vast complexities of human life and consciousness just the macro-level result of tiny spinning probability clouds desperately trying to find their most stable energetic state?
Now that is a thought that makes the empty space of the universe look pretty profoundly beautiful. Keep questioning the invisible. We'll see you next time.